Let's do chapter 18, problem 1. So we're on page 506, number 1. So a reading of the problem. Until recently, experimental results for the Hubble constant ranged between 50 and 100 kilometers per second per megaparsecs. Calculate the age of the universe for both of these extremes. Do you see any potential conflicts with other astronomical observations if h had been either of these numbers? First, let's explore the meaning of h. If we have an expanding universe so that everything moves away from the point of any observer, then the further away that the object is, then the faster it will be moving. And the velocity is proportional to the distance that it is away, and the constant of proportionality is a Hubble constant. So the things that are further away are moving faster. Now, following the development in astronomy by the numbers on page 484, in general, if something is moving at a constant velocity, then its distance is equal to the velocity that it has times the time that it goes. And if we put this into the Hubble law, v equals hd, then we replace distance with vt. We have v equals h, v times t, and the v's cancel out, and we have that 1 is equal to ht, which means that t is equal to 1 over h. So the age, or the amount of time with which these objects are separating, is the reciprocal of the Hubble constant. So 1 over the Hubble constant then gives you the age of the universe. Now this is a simplistic derivation because it assumes that the galaxies are moving apart with a constant velocity, which they are not actually, but it's okay for openers. So we have that h over t is equal to some constant. H times t is equal to some constant. Now also on page 484, it is derived that if we use the present assumed value for h, which is 70, then that will give us an age of the universe that is 14 billion years. So 70 times 14 billion years is equal to some constant. So if we say that h times t is a constant, then if we change h to some other h, we will change t to some other t, and if we change h to some third h, we will change t to some third t. So we know by the calculation on page 484 that h times t is equal to 70 times 14 times 10 to the 9th. Now in our text, they want to change that to a Hubble constant of 50. So that's going to generate a new time. So if we divide both sides by 50, we get 70 over 50 times 14 times 10 to the 9th is equal to our new time. And this would be 7 over 5 times 14 times 10 to the 9th equals our new time. And 5 into 14 is just about 3, a little bit less than 3. So then this would be 3 times 7 would be just about 20. So we would get an age of 20 billion years if the Hubble constant was 50. The trouble with an age of 20 billion years is that we don't see anything in our universe that's anywhere near that old. We see stars that are 13 billion years old, but we don't see anything that is anywhere near 20 billion years old. Now let's look at the other time. We also have that 70 times 14 times 10 to the 9th is equal to h3 times t3. where we're now assuming a different value for the Hubble constant, and we want to find the time that goes along with that one. So 70 times 14 times 10 to the 9th, and the value we want to assume now is 100, T3. So we divide both sides by 100, and we get 0.7 times 14 times 10 to the 9th is equal to our new time. And 0.7 is equal to 4 sevens are 28, and 9.8. So 9.8 times 10 to the 9th is our new time. Now the trouble with a universe that's 9.8 billion years old is that we already see stars that are 13 billion years old. So this is too young. So a Hubble constant of 100 gives you a universe that is too young. A Hubble constant of 50 gives you a universe that is too old.